So here we are in Chapter 20, Section 4. The section's entitled Cell EMF Under Standard Conditions. And to follow along with this, you're going to need some note paper. You're going to need a pen or a pencil. I encourage you to have your book available, open to Section 20.4, because then you might be able to see the pictures better than in the video. And you can have a calculator. More importantly, probably a periodic table, one of these, so then you can look at it better than you'll be able to see in the video. Pause the video now if you don't have those things. Where are we? Where are we? Well, first of all, in this chapter, we learned that we're talking about redox reactions, and that redox reactions transfer electrons. This transfer of electrons can be illustrated by half reactions, and we use these half reactions to balance these redox reactions. We want to be able to capture this electron transfer that occurs spontaneously. And if you remember back from chapter 19, spontaneous means that it has a negative delta G. Negative delta G. The Gibbs free energy is negative. We'll talk about that a lot today. We can capture these electrons that are transferring through an external circuit. Can capture this electron flow through an external circuit, and when we do that, we create what's called a galvanic or a voltaic cell. A galvanic or a voltaic cell. You should be able to use those two terms interchangeably. This means that we've set up two redox half reactions that have a transfer of electrons going between them, and we've labeled one of the half cells the anode. That's where oxidation takes place, anox, and the cathode is where reduction takes place, red cat, if you forgot that. And the other critical thing that we need for the external circuit of a redox reaction to take place is something called a salt bridge, so we can have a migration of ions between these. Write these things down because this will tell you what is expected of you to know so far. Where are we going? Where are we going? Where are we going in this video cast? First of all, we're going to find out why it's spontaneous. Second of all, we're going to talk about units for this electron transfer because there's a certain amount of energy going on here. And we're going to look at a half reaction rating scale. We're going to look at a half reaction rating scale, and we're going to find out, hey, which half reactions have the most potential or the most possibility of transferring electrons. Write these guys down. Make sure you've got some more paper out because we're going to go through about 5 pages of notes here, and I want you to write them all down as we go through this. So, to answer the first question, why is a redox reaction spontaneous? Well, first of all, because its G is negative. Because its G is negative. Remember in chapter 19, we talked about how we could calculate delta G several different ways for a reaction. In G equals H minus TS, well, it's either exothermic and its entropy is increasing, or one of the two is overtaking the reaction. So, since G depends on H and S, these two things combo together to give us a negative delta G. It's a spontaneous reaction, plain and simple. You can think of these redox reactions as being like a waterfall. It's being like a waterfall. We've got a river flowing along here, and then all of a sudden, bawoosh, it falls over the edge and the river's down here. There is water at a certain level here, and then there is another part of the water here. This height difference right here, is what the water molecules or the water particles have to go down. And the water or the electrons in a reaction flow from a higher energy level to a lower energy level. In physics, we call this difference in energy levels right here due to height potential energy. And we call it the same thing in a redox reaction like this. We say that some electrons are of a higher potential, in a particular half reaction, have a higher potential energy than other ones. And these electrons spontaneously flow from the higher energy level to the other lower energy level. We say that there is a potential energy difference. Potential energy difference. And sometimes we just drop the word potential and we just call it an energy difference. Sometimes we drop the word energy and we just call it a potential difference between one half reaction and another half reaction. So think of it a lot like a waterfall. The electrons spontaneously fall from one thing to another. The higher the waterfall, the more energy difference or potential difference there is between those two reactions. This potential energy difference is measured in volts. Measured in volts. Volts are an amount of energy per unit charge. Amount of energy per unit charge. And a volt is defined as a joule per coulomb. 1 joule per 1 coulomb. And remember, when the word per is used in mathematics or in chemistry, we always mean divided by. Joule per coulomb. What is a joule? Well, a joule, if you remember, is a kilogram meter squared per second squared. Maybe you didn't remember that. But it is a unit of energy. Okay? It's an amount of work. It's an amount of force per unit time. It's something that's falling and bouncing and pushing and shoving, and it's energy. Energy. You doing something. In this case, it's the electron doing something. What is a coulomb? Well, a coulomb is a really strange word, and I want to talk about this for just a second. A coulomb is what's called a unit of charge. In this case, it's negative charge because it's electrons that are falling. Okay? 1 electron has 1.6 times 10 to the 19th coulombs of charge. Or, as we'll learn later in this chapter, approximately 96,500 coulombs are the amount of charge in 1 mole of electrons. So in 6.02 times 10 to the 23rd electrons, there are 96,500 coulombs of charge. It's an amount of negativeness. So we have a certain amount of energy per amount of charge that we have. You can think of the voltage as being a triangle, the JVC triangle. Volt equals joule per coulomb. If you want to solve for voltage, it's joule per coulomb. If you want to solve for joules, it's volt times coulomb. If you want to solve for coulombs, it's joule per volt, joule. Yeah. So anyway, this little triangle right here is a handy thing to write down because it's not in the book anywhere. It's not in the book. Well, this energy per unit charge is called about 10 different names. Lots of different names for this. And why they give so many different names for it has some actually interesting history, but we're not going to go into it. I'm just going to bottom line say that there's a lot of different names that mean the same thing. And you've seen this before in chemistry. There's a lot of different ways of describing the exact same thing. And so I'm going to give you a whole bunch of them right now. And you just need to know that, hey, they're interchangeable. This energy per unit charge is called the force pushing electrons. That sounds kind of strange, but that's what it is. It's the thing that's pushing the electrons. Some people call it the electron moving force. Or if you want to get really fancy, they call it the electromotive force. Electron moving force. But, they want to call it electromotive because that sounds really fancy. Since people don't want to say electromoving or electron moving or electromotive force all the time, they sometimes come up with an abbreviation. They call it the EMF. EMF. That stands for electron moving force or electromotive force. EMF. Okay, that's the energy per unit charge. Some people call it the potential energy. Some people call it the galvanic or the voltaic cell potential. Because if you remember, we can actually take two half reactions and stick them together and we make what's called a galvanic or a voltaic cell. They call this potential energy that it has the cell potential. Some people just call it the voltage. They all mean the same thing. They all mean the same thing, and they're all interchangeable, and they're all used lots of different times. Okay? Now, if these things if these names occur at 25 degrees Celsius and 1 atmosphere with 1 molar solutions, now you can put the word standard in front of each one of these things. You can call it the standard force pulling electrons, the standard electron moving force, the standard electromotive force, the standard EMF, the standard potential energy, the standard cell potential, the standard cell voltage. Get used to that because this word is used all the time. They call it the standard cell potential, the standard EMF, the standard voltage. So what are the symbols for this? What are the symbols for this? You know, you don't want to write out the word standard cell potential all the time. So what is the standard symbols for electromotive force? E. E is sometimes used, okay? E. If it's at standard conditions, it's E circle, because remember the little circle means 25 degrees Celsius, 1 atmosphere, 1 molar solutions. E cell, okay, because it's in a galvanic cell, and they'll put a little circle here if it's at standard conditions. EMF, and they'll put a little circle right here because it's the electromotive force, okay? At 25 degrees Celsius in 1 molar solution, they put this little circle right there for all of these, okay? This fancy looking E right here, I'm going to write that again so you can see what that is. Sometimes you'll see an E like this, and then they'll write like EMF, and they'll put another little circle here. Okay? Or sometimes you'll just see a V, V for volts. They'll put a little circle up above here. Sometimes you'll just see an E like this. On your periodic table underneath electrochemistry, you'll see that they put, I'm going to zoom in on this right here, they just use an E with a little cell right here, E cell, okay? And then when it's at standard conditions, they use E with a little circle right here, okay? That's on the yellow periodic table. You can see it used right down here too, E with a little circle, okay? That's what that means. Be used to those kind of symbols because there's lots of different ones, and you see them all used interchangeably. All right, next. So how much potential does a particular reaction have? So, for example, we talked last video cast about this reaction, zinc and copper. We took a zinc chunk and threw it into some copper nitrate solution. We got the zinc to oxidized and the copper solution to the copper ions to be reduced to copper. Okay, notice I put aqueous and 1 molar, aqueous and 1 molar. Why do you think I put 1 molar down there? Because it's a standard condition, right? 1 atmosphere, 1 molar solution, 25 degrees Celsius, all of those things. Well, this particular reaction right here, where zinc is oxidized and copper is reduced, actually has a cell EMF, or a cell voltage, or a standard cell potential of 1.10 volts. Now, how do we know that? How do we know that? Well, I'm going to explain it, but it's going to take a few minutes. Notice how we have in this reaction actually 2 half reactions. We have zinc going to zinc plus 2. This is an oxidation reaction, and therefore it is the anode of our cell. Copper plus 2 going to copper. This is reduction, and so it's the cathode of our reaction. Remember, anox, red cat. You should be able to define these and pick these out really quickly. The galvanic and the cell potential depends on the particular anode and cathode of the reaction. And in this case, we have zinc as the anode and copper as the cathode. The E cell, or the EMF, or the voltage, or the potential difference, remember all those words mean the same thing, of this particular reaction is the difference between the 2 half reactions. Now, in mathematics, what does the word difference mean? The difference means subtraction, right? So there's an equation that helps us find this. There's an equation that helps us find this. The equation that helps us find this is that the E of a particular cell, the EMF of a particular cell, is the potential of the cathode's chance to be reduced minus the potential of the anode to be reduced. Notice how it's a minus sign right here because it's a difference between these two. Where do I find out the potential for the cathode? And in this case, it would be copper being reduced? And where do I find out the potential for zinc, in this case the anode right here, to be reduced? Well, they're tabulated for us. And there's a big old reference scale on this table called the standard reduction potentials. Now read those words really carefully. Standard means 25 degrees Celsius, 1 atmosphere, 1 molar solution. Reduction potential means possibility or potential to be reduced. Potential to be reduced. You have a huge table of these on the yellow periodic table. These are called the standard reduction potentials. These are the voltages for a whole bunch of half reactions, a whole bunch of them. And you'll notice if you look really close, and I'm going to zoom in, there is one that's actually arbitrarily assigned 0 volts. You can see right here the 0 voltage one is the one that produces hydrogen. And you'll see that all of these standard reduction potentials right here, all of these are equations that are written as the gain of electrons because they're called reduction potentials, and reduction is gain. Remember RIG? Reduction is the gain of electrons. So we could look on there and we could find the potential for, in our case, copper to be reduced, which is our cathode, and the potential for zinc to be reduced. Even though it's being oxidized in the reaction, we're still going to look at its reducible potential. Put those two values in here, subtract them or find the difference, and then we would know the potential difference of the cell, the voltage of the cell, and it would turn out to be 1.10. Notice I said that 0 volts is assigned to the hydrogen half reaction. 0 volts is assigned to the hydrogen half reaction. This is arbitrarily done, and it was done many, many years ago when electrochemistry was first standardized. And the hydrogen half reaction is where there's 2 hydrogen ions, aqueous 1 molar solution, plus 2 electrons, goes to H2 gas, 1 atmosphere. Notice it's all standard conditions, and this was given a standard EMF of 0. Standard EMF of 0. This is called the standard hydrogen electrode, or for short, they call it the SHE. Standard hydrogen electrode. Well, what does this thing look like? Look on page 862 of your text right here. The standard hydrogen electrode actually has a picture right here at the top of the page. I'm going to zoom in on it a little bit. I'll read about it for just a second. Notice that a standard hydrogen electrode consists of finely divided platinum wire in contact with hydrogen gas at 1 atmosphere and an acidic solution with H plus equal to 1 molar. So we've got H2 gas in here. We've got H plus as a 1 molar solution. Okay. Now the platinum doesn't do anything except allow the flow of electrons in there. The hydrogen atoms bond together to form H2 when the SHE is the when reduction occurs. Okay. When the SHE is the anode of the cell, the reverse process occurs. A H2 molecule at the electrode surface loses 2 electrons and it's oxidized to become H+. The H+ ions in the solution are hydrated, so really they're H3O pluses right here. Okay? So the standard hydrogen electrode actually has some stuff written about it on the page before. If you want to read more and know more about it, it's right down here, and it talks about an electron designed to produce the half reaction right here, known as the 0 voltage reaction. It's called the standard hydrogen electrode SHE, or normal hydrogen electrode NHE. A standard hydrogen electrode consists of platinum wire, piece of platinum foil covered with finely divided platinum that serves as an inert surface for the reaction to take place. Okay, so now you've seen a picture of it. You can actually see the reaction on the atomic scale right here. And you can see that it has assigned a voltage of 0. Picture caption on page 862. We looked on the yellow periodic table and we saw that it had 0 voltage assigned to it. Since the hydrogen electrode is assigned a 0 voltage, we can use it along with all the other standard reduction potentials to calculate the EMF, or the cell voltage, of any combination of half reactions. One last thing about these, though, the standard reduction potentials are in joules per coulomb, or in voltage. This is an intensive property of matter. And if you forgot what an intensive property is from way back in chapter 1, an intensive property is one that is independent of the amount of stuff that we have. So therefore, changing the stoichiometric coefficient of a reaction does not affect the value of the standard reduction potential. If you want to look on the bottom of page 863 of the 10th edition, they actually have the zinc half reaction, Zn plus 2, the one that we're actually asking some questions about here, aqueous, 1 molar, plus some electrons goes to Zn solid. And then the way that they balanced it was they put 50 zincs, 100 electrons, and 50 Zns solid over here. This is solid. These are, electrons. And then this is aqueous 1 molar solution right here. So it's standard. But the voltage for this half reaction right here is still the same as the voltage where there would be a 1, a 2, and a 1 right here. If we look on here, we can find the zinc half reaction that shows zinc gaining electrons right here. Let me see if I can zoom in on it. There we go. Zinc plus 2 electrons. Arrow right here to zinc. And if you look over here, it's got a value of negative 0.76 volts. So the voltage is negative 0.76 volts. Whoops. Got to zoom way out on this one. Can't see anything that I'm doing. There we go. Negative 0.76 volts. Even though it has 50, 100, and 50, this is still the cell potential because it's independent of how much stuff that you have. Just so you have some. Just so you have some. Okay? So, going back to the very beginning question, almost 10 minutes ago or so, calculate the EMF, or the voltage, of this cell. I already told you what it was, but how would you go about calculating it? Well, first you got to know the half reactions. Zinc goes to zinc plus 2. Copper plus 2 goes to copper. Okay? So Zn goes to Zn plus 2. Notice this is oxidation. So this is our anode. And copper plus 2 goes to copper. This is our reduction, and therefore it is our cathode. And remember, to find E, standard conditions of a cell, what we want to do is we want to do E cathode minus E anode. Okay? And we look at the standard reduction potentials for each one of these. So the cathode right here is the copper reaction. The anode right here is the zinc reaction. And I need to look those two critters up on the standard reduction potentials page. So the copper one's actually up here a little ways. And there's a couple different copper ones, so you have to be really careful what you're looking at. Okay? You'll notice there's copper plus 1 plus an electron goes to copper solid. There's copper plus 2 electrons goes to copper solid. There's copper plus 2 plus an electron goes to copper plus 1. Well, which one are we actually looking for? Well, if you look at our half reactions here, and this is where it's really important to be able to balance a half reaction, notice we've got 2 electrons here, and we've got 2 electrons here. So we're looking at the copper plus 2. Zoom out again here. The copper plus 2 electrons goes to copper. Notice how zinc is also losing 2 electrons, okay? So we're looking for the copper plus 2 electrons goes to copper. And if I zoom in on that, the copper plus 2 going to 2 electrons right here, I won't zoom in on it, I'll just give you the value, is 0.34. So for the cathode, I've got 0.34 volts. And for the zinc anode now, we already looked this one up. The zinc's right down here a little bit lower. Zinc plus 2 electrons is negative 0.76. Now, I know that on this table, it's written backwards of what this reaction is. But remember, this table lists everything as reduction. I know because here it's written as oxidation, and so it's going to be the backwards of it on here. I still take the value that I get from right here, negative 0.76, and I put it into this equation, negative 0.76. And now I take 0.34 minus a minus 0.76. And if I do my math right, I think I end up with about 1.10 volts. That is how to find the standard reduction potential of a particular cell that includes an oxidation and a reduction reaction. Lots more examples of this next video cast, and you'll be expected to be able to do it fairly fast. Find these things on this table right here or in the back of your book, and then be able to find the E cell or the EMF or the voltage or whatever name you happen to give to it. By the way, the more EMF the cell has, the greater the driving force of the reaction. And we'll find out that G and E cell are actually related to one another in a little while. And, you know, the bigger the E cell, the bigger the G is going to be, or the more negative the G is going to be, because it's going to be more spontaneous, because there's going to be more driving force for the reaction, more potential energy, a bigger hill for that waterfall to fall over. So hopefully you learned a little bit about electrochemistry and where we get this spontaneous flow of electrons and how we calculate cell EMF. Next video cast, we'll look at calculating a bunch of EMFs, and we'll look at some specific cell calculations as well.